Hello students. This video is pre-recorded as yesterday I didn't record the first 35 minutes of the lesson. Now let's look at the homework first. Last week we have 3 assignments. I only marked 2. So the first assignment, the questions are easier. You just need to apply the differentiation rule directly. The mistakes are: question 1, dy dx is equal to 0. Although this function looks like a power function, it's not. It's a constant function. You should only use the constant rule. Question 14. This question, it's easier to split the fraction into 3 terms, then you don't have to use the quotient rule. The answer is this. Question 18, product rule. Question 23, quotient rule. Question 41, product rule. The last question, 43, I recommend that you simplify this original function before you differentiate. It's much easier as there are no negative index left. Okay, that's so much for the first assignment. The second assignment. These 4 questions are harder. For question 33. Now this solution provided by this answer, now you only have to expand the original function, and then you don't have to use the product rule. That's 33. 36, quotient rule. Now some students don't know how to write the quotient rule. It's d high, this part is high, low, minus d low, this part is low, times high, divided by low square. Now this one, pay attention, this part is not dy dx, it's d dx and this. Okay, you can write d dx this, or you can write d this, basically this is y, d this dx. It doesn't matter where you put it. It means the same thing, the derivative function. The answer should be arranged in the descending order, in descending power of x. 42. This is another notation where you don't say substitute x equal 4 into the derivative function. You just write dy dx or y prime and then the stroke x equal 4, and then you do the substitution. Last question. Y is a very complicated function. It's a product of a quotient. So if you want to differentiate this function directly, you would have to use the product rule and then later the quotient rule. To avoid that, we can expand and only keep the quotient, expand the product, like this. This is the standard solution, but you can also do it the other way. The standard solution, the product is expanded, and then you differentiate y with respect to t this time. So you write dy dt. Okay, dy dt, d high low minus d low high divided by low square. And then that's it. And then the simplified form. And then you do the substitution. Okay. Actually, when I mark your homework, I looked at your steps. Some of your steps are incorrect. So you have to do the correction. If your steps are incorrect, even if your final answer was correct. In last week's lesson, we left out example 10. And this is an example where product and quotient rules are both applied. Kind of like the question in the second assignment, the last question, question 44, kind of like that. Later, I made a video and uploaded, and not many view counts according to my stats. So here I will point it out again. In some questions, when you see the structure of quotient and product, you can apply them accordingly. So this question is d high low minus d low high divided by low square. That is the quotient rule. But inside the quotient rule, the first differentiation is easy. This one is easy, that's 3. The second differentiation is the product. Do you see? And then you apply the product rule here. Okay? And then in the next row, the differentiation is done. Now, this row, the differentiation is done. And then you will simplify and simplify and simplify. Now, sometimes the simplification takes way longer than the differentiation. That's very normal. And you still have to practice to do that. Now, after the simplification, you can put in x equal 1 and find out the result. There is a attached classwork you can practice. Before we begin today's lesson, let's talk about this question left out 2 weeks ago. This is the solution of that question. It's in the notes 5.1 POP exam questions 2018 HKDSE. Last week I gave you 5 minutes to finish this question, but only a handful of students completed. And then I asked you to practice at home yourself, and here is the answer. First, you need to express f of 1 plus h in terms of h, and that is the answer. In this answer, you can see the polynomial part and the exponential part are separate. You should not expand. And then find f prime 1, the derivative, the value at x equals to 1. So according to the first principle, at x equal 1. And then I will do the calculation as follows. Now this question was very difficult that year because a lot of students used another first principle, this one, the right hand side, this one, which is not wrong because this is the first principle to find the derivative function. Whereas in this question, what you should do is to use the first principle to find the derivative. They are obviously of different difficulty level. You see, this one is much more complicated. No, I don't think it's maybe with enough skill and practice, maybe it's possible. I'm not saying it's not possible. It's possible to find the derivative function and then do the substitution. But you can see it's harder, okay? Now, I want to point out the difference between first principle and differentiation. In first principle, you can do the substitution first and then find the derivative. You can also find the derivative function and then substitute. But in differentiation, you cannot. You cannot say, oh, I want to find the derivative at 1. I put x equal 1 into the function first and then I differentiate. It doesn't work that way. I just need to point out that. Now, if you want to practice a similar question like this, the next question, 2019 HKDSE, is very appropriate. You can find out and then check the answer online. Now let's come to today's lesson. Now today we only learn one rule. It's the differentiation of composite functions. Now, I think last week the rules that we learned, one of them, the power rule, is designed specifically for a function, designed for power function. The other rules, the additional rule, the product rule, and quotient rule, they are not designed by functions. They are designed by the structure of the function, not the type of the function. This differentiation rule today is designed for these functions, composite function. Now first we need to understand what composite functions are. A composite function basically is to put a function inside another function. In simple, I will have, this is a function h, and this is another function g. I will put h inside g. An example in the past would be this one. G of x equal to x, that's a function. And x squared is another function. So if I put x squared inside this one, then I get a composite function. Do you know what I mean? Because I put another function inside the original function, I create another function. The result is a composite function. I'll give you another example. Another example is sine square, sine x squared. Now sine x is a basic function. Sine x squared is a composite function. Why is it a composite function? It's put sine x inside something square. Thus, the square is a function, and then you put sine inside. So that's a composite function. Another example here, square root log x. Don't be alarmed. This is just log to the base e. So square root log x. Now, we know square root is a basic function. Log x is also a basic function. But if you put log x inside square root, that's a composite function. Last example. E to the power x squared is a composite function. Because e to the power x is exponential, that's a basic function. But if you replace x with x squared, that means I put another function inside this function. So that's a composite function. Okay? So a lot of functions can be composite function. Okay? You have the original function and then you have another function put in, and that's a composite function. So let's read the rule. The rule is called chain rule. So you have two functions, y equal g of u and u equal h of x. They are two differentiable functions. Now you always see these conditions because otherwise we cannot differentiate. So that's always there. In all the differentiation rules that we learn, these conditions are always there. They always have to be differentiable to have these properties. So they are differentiable functions. And the composite function, you see the composite function is g of h of x. Now, that is to replace u with h of x. I put h of x inside g. That's a composite function. This composite function is also differentiable without doubt. If two of them are differentiable, the new function, the composite function, is also differentiable, and the derivative function, dy dx, is equal to the derivatives of two functions and then multiply. Let me see. The first derivative is dy du. What does dy du mean? Dy du means the outside function g prime, but not dx. It's dy du, so it's g prime with respect to u. The second derivative is du dx. U is equal to h, so this one is equal to the second function prime, h prime, with respect to x. Okay? I know. Look here. This is one example. In the first example 11, I will show you very detailed steps so you can follow what chain rule means. Later on, I will speed up and skip some steps. But for the first example, part A. Now, first I observe a composite function, y equal u squared, and u is another function. It's an outside and an inside function. Now, how do I find dy dx? Now, dy dx is two derivatives and then multiply. So I need to find the first derivative, dy du. This is y prime with respect to u. So dy du 5u4. Second derivative, this one, du dx. And then I find out du dx. And du dx equal x to the power negative 3. Now the final answer, dy dx, is to use this result multiply the second result. That's 5u4 multiply x negative 3. And then in your final answer, you just replace u with the expression of x because the final answer shouldn't have u in it. U is a disposable product in the process. We use it, and then the final answer should not have it. So you just replace u with x, and that's it. That's the answer. Another example. This example is y equal u to the power negative 1 over 2. That's the outside. And u equals something x minus 2x squared. Okay? Now first I'll differentiate the first outside function, dy du. Now sometimes I write y prime. Sometimes I write dy du, and you can see clearly the first notation is much better. Because the second notation I don't know with respect to what. You have to say it. And the first notation is very clear. It's not dy dx, it's dy du. So dy du with respect to u is negative 1 over 2 u to the power negative 3 over 2. Second function, du dx, is 1 minus 2 times 2x equal 1 minus 4x. The final answer, dy dx, is dy du, write it down, and then du dx. Write it down. The final answer, you replace u with x, and that's how. That's how. Now this comics was from a very long time ago, but it kind of explains how this works, because this is this pregnant lady, and inside her body there is another function, the baby. And for the chain rule, basically you differentiate the outside and then you differentiate the inside. I hope this comics makes sense to you. Now finally, let's look at the proof. The proof is short. I think it's shortly written like this. You just need to divide something and multiply the same value. In my mind, I think the result of the chain rule is much more interesting than the proof of chain rule. That's all. That's all. For the rest, I think you can watch the video from last night. See you next time.